Cheers, Rob. Thanks a lot.
Yeah, thanks.
And yeah, thanks for coming to the talk. So everyone had a good conference so far today? Yes, lots of smiling, nodding going on. Yeah, it's been a great day so far. So yeah, cheers to Wargaming for arranging everything. So, okay, on to some introductions. So I'm Will Augar. I'm the lead audio programmer at Frontier.
And I'm John Ashby. I'm an audio programmer at Frontier.
So yeah, Frontier Developments, a studio based in Cambridge in the UK. Here's some of our recent games. We have Elite Dangerous, Planet Coaster, and Jurassic World Evolution. So yeah, as I say, Frontier's based in Cambridge. There's about 400 of us in the studio now. This is us in our shiny new Cambridge office, which we moved into earlier this year. We develop and publish our own games. So, and we kind of work on multiple projects, and this is us all here, smiling away. Okay, so the most recent game we released, as I said, Jurassic World Evolution, came out in the summer. So let's start off with a fun trailer from the game.
You think that things are going to turn out differently, huh? Well, the ones before you did too. Because they believed that they were in control. And control, well, here's the thing. Humanity is desperate for it. We are seduced by it, deceived by the illusion of it, but we never really possess it. Because if there's anything that chaos theory has taught us, it's that nature is on its own course. And when we interfere, when humanity tries to put nature into orderly boxes, chaos destroys them. And what makes us such unique creatures is knowing the scope and power of what we're up against and still believing that we can win. I know, however, what I would predict.
Okay, thanks, Jeff. So just a quick overview of the talk for today. We're going to look at the voice problem, sort of define the problem. Then we're going to have a look at some of the middleware solutions that are available and some of their shortcomings. Then we're going to discuss the custom voice management systems that we've developed at Frontier. This will be the main bit of the talk, really. And we'll try and leave a good amount of time for questions. So if anything comes to mind, please store it up and ask it at the end. Okay, so the voice problem. So before we talk about the problem, let's just define a voice. So a voice is really just a playing sound. That's what we mean when we talk about a voice. Actually, I was just going to ask, who here does game audio? Like, raise your hand if you do game audio. Okay, some game audio people in the house. Good to see you. Yeah, so let's have a think about when there are too many voices in the game. So we run into problems in these two main areas. Performance problems, first up, and then aesthetic problems. So the performance problems of having too many voices playing comes from the fact that voices are really the main use of CPU time for audio. So that's really where we're spending our time on the CPU. We're sharing that time with the rest of the game, of course, but voices are really where we're spending it. And because we're sharing it with other things and CPU time is finite, we have to manage it. We can't just go, adding more and more voices. That's not going to work. And when we have too many voices, we run out of time. We can't process the voices. We get big audio clicks, big audio dropouts, terrible, horrendous. We don't want that. We need to fix this problem. So on the other side, we have the aesthetic problems of having too many voices playing. Put simply, if you have too many voices playing at once in a game, then you get a really muddy mix, right? Like the beautiful sound design that the team's worked on, that's not going to really shine through. We're not going to get the emotional content that the sound designers put all this effort into is going to get lost. It's going to get muddied. Too many voices playing at once. Okay, so that's the problem. We definitely need to solve this. But before we look at how we solve it, we need a way to evaluate our solutions. So, well, the clue was in the title of the talk. We need it to run fast, sound great, but there's one more thing. We need development costs to be low. So, you know, it's no good coming up with an elaborate system that's going to take 5 years to make, that we need to re-implement for every game we make, or that makes it really difficult to just hook up audio into the game. No, we need the development cost, the amount of time it takes to make this solution, we need that to be low as well. Okay, so let's have a look at middleware solutions. So the two market leaders, Wise and Fmod, both provide voice management. So just hands up if you use Wise. People familiar with Wise? Yeah, okay. So this is like the main, I would say it's the market leader over Fmod, but that's the solution, the middleware that we use at Frontier. So we're going to sort of focus on Wise in this talk. Now, in Wise, sound designers use the authoring tool to manage voices. They get to set behaviors, they get to set priorities, they get to set up quite elaborate hierarchies of priority and what overrides which, and all this kind of mechanism. But basically, it's the sound designer's job. They use Wise's authoring tool to manage voices. Okay, so Wise is great. Like, let's just be clear here. It's a fantastic piece of middleware. It enables sound designers to create fantastic interactive audio, and they can work. They don't need the programmer to help them do every little thing. They can work autonomously. We don't want to replace Wise, but it does run into shortcomings with regard to voice management. So the first problem with Wise is basically virtual voice performance. So in Wise, when virtual voices really start to stack up, and here I'm talking, you know, when you have maybe 1,000 game objects or more, this starts to become quite crippling, actually. And Audio Kinetic, the developer of Wise, they give you advice. They say if you have more than 1,000 game objects, well, you just need to manage that. So we need to come up with a solution if we have more than 1,000 game objects. Okay, so the other sort of shortcoming with middleware is the voice management is like really intertwined with the sound design. So this means that if you run into a problem with the number of voices stacking up, and you need to make a change, well, that might impact how you've done your sound design, how you've set things up in Wise, and that's really difficult problem to manage. You know, you're kind of intertwined, and if you need to make one of these changes late in the day, then it's difficult. So the next thing is really that in Wise, it's actually quite unclear as to what's happening at runtime. So you set everything up in Wise, you're running your game, you've got your busy scene running, but you know, you can't really see what it's doing. It's quite unclear as to what's virtual and what's not. Why is it making those decisions? There is some UI in Wise that sort of shows you a list of virtual voices, etc. But it's hard to see how things are moving dynamically, and that turns out to be quite important during development. Okay, so those are some of the problems in Wise. We've been developing custom solutions, but our solutions are written on top of Wise. So we use the sound engine API, and we're dealing in emitters and events, not raw voices, because that's the main the context that Wise is written in. So we're writing this system on top of Wise. Okay, let's have a look at how we've developed these solutions over time. This has been like an iterative process. So we've been developing solutions for 5 years or so. Each game, we kind of look at what went before and build on it, and kind of move things forward for the next game. And that's been the case, for 5 years or so. So back when we started, we didn't really have a system. We were just doing ad hoc voice management, usually in a sort of firefighting style when the project really needed it. We didn't really have a system. So the main takeaway here was we actually need a system. So on to Elite Dangerous. For this game, we made several generic systems that were, dealt with voice management, but these systems were quite brittle. So every time we needed voice to be managed in a different way, we had to write a new system, and we ended up with like multiple voice management systems, which wasn't ideal. So the takeaway really was we need to be able to customize our voice management systems. So that brings us to Planet Coaster. So for Planet Coaster, we wrote a very flexible voice management system. It led to a great sounding game, like Elite, but here we could really go to town on voice management, get it just right for all the different scenarios in the game. But the downside here was we wrote a lot of code to do this. We had a lot of custom solutions for the different parts of the game. And the takeaway from this development was we need to reduce the dev costs. That was the key thing. So that brings us to Jurassic World Evolution. So the aims here, when we came to this version, were to maintain the performance and the aesthetic gains that we made on the previous games. Like, we wanted it to perform well. We wanted it to sound good, as Elite and Planet Coaster do. But as I said, we needed to bring that dev cost down. So this sounds like quite a tricky. Quite a sort of a tricky thing to do, but we need it to be generic where possible, but customizable where needed. That was the thing here, really. We needed the best of the Elite and Planet Coaster systems together. So this was quite a sort of, we thought long and hard about how to achieve this balance of things, and we turned to some programming best practices to help us here. So the first of which is don't repeat yourself. And the idea here is that you only want to write one piece of code once and then reuse it. You don't want to keep writing it again and again, re-implementing the same thing. So, for example, the code that virtualizes your audio objects, you just want to do that once and use it across the whole game. The second programming best practice that we took on board was this idea of separation of concerns. Now, the idea here is that you want each piece of code to be doing exactly one job. So the code that sorts emitters, so the highest priority ones come at the top of the list. You want that to only do that sorting job. The code that triggers events, well, you want that to only do event triggering. You don't want to mix the two. The two systems have to have a separation of concerns. And one way to check if you've separated your concerns correctly is, can you give a good name to each part of the code? And if you can give it a good name that just describes really, precisely what it does, then great. Separated concerns, that's a good thing. Okay, hand over to John.
Cool. Could everyone hear me still? Yes, fantastic. Yes, I will not use the clicker because I'm suspicious of it. So we've just heard that we want to separate our concerns. We're building a voice management system, so our concern is really with voice management. We want to separate things within that, but we really want to separate that from voice triggering as much as possible. We don't want to care, why is this particular sound playing? We're really trying to build a system that answers this question: what sounds do we want to hear? And I think it's easiest to illustrate this with a concrete example. So here's a scene from Jurassic World. You've got a helicopter in the top left, you've got a T-Rex, you've got a few smaller dinosaurs, and you've got a car. And you can imagine posing this scene to a linear sound designer, like a sound designer on a film, and saying, okay, what sounds do you think we want to hear in the scene? You can give them like a DAW with a track for every sound in the scene and say, make sure we're hearing the important sounds. And they'd probably mute whatever they thought wasn't important. And when we're building a voice management system, it's almost like we're building an artificial intelligence. We want the voice management system to give as close a possible answer to one a linear sound designer would give. That's our goal. But we're not doing linear sound design. We're in games, we're in interactive audio, so we need an answer for every possible scene that could ever occur, even the ridiculous scenarios that QA will come up with. So the way that we found really useful was to make rules about what's most important. And when we define these rules, we found it really, really useful to define them in a natural language. So phrases like, we want to hear, we don't want to hear, this is more important than that. Wise sort of by default uses this numeric sort of system, like 65 and 12, and when a sound designer and a programmer are talking, if they both have to translate their thoughts into this abstract space, then it just leads to confusion. If a sound designer can say, I want to hear the T-Rex, and I can implement code that makes sure we hear the T-Rex, that's much clearer, and we're going to end up with a much simpler system. And when we're building these rules, we also want to go back to that separation of concerns. We want to have simple, small rules that are understandable, that you can say in a single sentence, rather than big rules that no one really understands and break in interesting and fun ways. So we found the best way to separate our concerns is to divide sounds into categories and have rules for each. So we've got dinosaurs and we've got vehicles, so we'll have some rules for dinosaurs and we'll keep them separate for vehicles. And just as a sort of an implementation detail, these categories that we've come up with, they can be part of the mix tree in Wise, but you don't have to make them tied to the mix tree. So if we've got some foot plants, and they're currently part of the dinosaur mix hierarchy, if we need to change the filtering on them and move them to the physics bus, we don't want to change that category because we want the same rules to apply. They're still important, even if they're mixed slightly differently. So when we're writing rules about dinosaurs, we're trying to answer this question. Which is the more important dinosaur? Which one do people think? The small one or the big one that's T-Rex? So we could say it's the closest dinosaur. And we might say, you know, if you can't see it, it's not important. And we might add some other rules about it being a predator later. And all those rules that we write about dinosaurs, we want to keep them completely separate from rules about what's the more important vehicle. Because the more important vehicle in a scene might be the fastest vehicle, right? If it's whizzing across the screen, it's what your eye's drawn to, it's what you want to hear. And when we separate these rules into categories, it means you never have to answer the question, is this dinosaur more important than this vehicle? Because that's quite a complicated question to answer, and you might need a very bug-ridden system to answer that question. But if you can make it simple, is this dinosaur more important than this dinosaur? That's really good. We found that really valuable. But you're probably also going to have some other rules about the balance of categories. You know, how many dinosaurs do we want to hear in a scene? Just 1, 4, 10,000? And similarly, you know, how many vehicles do we want to hear? Do we just want to hear the most important vehicle, or do we want to hear a few? And you can combine all these sort of balance of category rules into a nice one-sentence summary. You know, in this game, we want to hear 4 dinosaurs and 1 vehicle. And that's a really powerful statement that you can say to a sound designer when they come on the project, this is our vision. This is what we want the game to sound like. So how do all these rules that I've sort of talked about vaguely, how do they combine? How do they make sure we hear what we want to hear? Well, let's take our scene from before. Let's split it up. So we've got a sort of sound for every source in the scene. You know, we've got the dinosaurs and the helicopter. And then we'll group them into our categories. So we've got dinosaurs, vehicles. We have our rules about how many dinosaurs and vehicles we want to have, and our rules about what's a more important dinosaur and vehicle. We'll rank our dinosaurs based on our rules about what's more important, and then we'll sort of start spending our budget. We want to hear 4 dinosaurs, we want to hear the 4 most important dinosaurs, so the 5th most important dinosaur, we'll mute it, it's not important. And similarly for vehicles, we'll mute the slowest vehicle, because that's the least important. But this is game development. We'll implement the system, a sound designer will listen to it, and they'll want to change something, right? We want to build a system that can adapt to that change because it is going to happen. So the sound designer might say, I want to hear less dinosaurs. The mix is too cluttered, I can't really tell what's going on, I just want to hear less dinosaurs. And when they said, I want to hear less dinosaurs, they didn't say, I want to hear less dinosaurs. And as a consequence of that, on level 4B, I would like to hear more vehicles as well. When we make one change to a voice management system, we want to have exactly one outcome, and we want that to be predictable. So what rule do we think we might want to change? Well, we could change the rules about how many dinosaurs we want to hear, and then we'll hear the 3 closest dinosaurs, so we'll mute that T-Rex. Sound designer listens to it again. Can't hear that T-Rex that's stomping around and mauling people. They're probably going to say, you know, I want to hear the T-Rex. I don't care that it's far away. It's the most important thing to me. I want the player to hear that T-Rex. So we add a new rule. We can add rules to accurately represent what's important to the player. So we add a rule saying the closest predator is more important than all the prey. So we mark it as a predator, we move it to the top of the list, then we hear that T-Rex that's important, and we hear the 2 sort of smaller dinosaurs, but we don't hear that 3rd dinosaur because we want a clean mix. Okay, so that's sort of our customization points, how we can make this system play the sounds that are important. But what we learned from Planet Coaster was we need a generic framework that we can plug these rules into with a simple way that has a low development cost. So we've got our triggering code on the left, which is the concern that we're not really thinking about in this talk. That's, you know, when this dinosaur plays this animation, play this roar, or, you know, when this physics event happens, do this other thing. We're just going to imagine that that's like a block that will tell us things like play this event, set this parameter, set the switch. That's our abstraction. We're a voice management system, and our job is to decide, okay, for these events, what do we want to hear? And if we want to hear it, we'll pass it to our sound engine, which in our case is Wise, and it'll start rendering it, and the player can hear it. But if we passed everything along to our sound engine, it will use this Wise virtual voice, which would start using up a lot of resources. So we want to basically not push anything to Wise that we don't want to hear. So this is a bit of a clickbaity title, but I think it adequately represents what the content of the slide is. So how to get 20 times the performance of a Wise virtual voice with one simple trick. In the initial draft of this, you know, I had 18 pages of ads. Like, we went through like how Jessica Alba was involved, but I sort of cut that out for this, the final version. Yeah, so what is this trick? How do we get all this performance? We use a cache, okay? Event comes in from triggering, physics has happened, whatever. We cache it. We put it in a in-memory cache. We say, this event happened at this time. This parameter was set at this time to this value. And because it's just an in-memory cache, it's very efficient, very quick. That update takes, you know, microseconds, if that. And then if at some point in the future we decide, okay, this event is important, maybe it's that T-Rex, we want the player to hear it, then what we can do, so we've got it in our cache, we decide we want to hear it, so we replicate it to Wise. We say, okay, post this event, play this sound, you know, seek into it 2 seconds or whatever. Wise will then start rendering it. It'll start making that noise or whatever it is. I can tell I'm a professional sound designer because I can make dinosaur noises. So the player will be hearing it. We decided it's important. But just as equally, if we decide it's no longer important, we can sort of break that switch to the sound engine. We can just keep it in the cache. We can kill all the voice in Wise, and it'll be really performant when it's just using that cache because it's just updating what's happening. And you know, not every system will need this. I think when you sort of break through that 1,000 voice barrier, this is when this becomes really, really important. But if you do decide, you know, this is what we need, it's really, really important to write this code exactly once. Don't repeat yourself, right? If you write this code every time you have a new feature, you'll have a really high development cost, you'll have lots of bugs, and you'll have lots of late nights. So if you are going to do this, write it once. Cool. So this is sort of how, a bit more expanded, of how the voice management system works. So the dynamic audio object was what we call this thing that does the cache. So we're going to have a number of those for each sound source in the scene. And we want the budget and recipe to basically rank them from most important to least important and sort of have the number that we want. And that's the budget and the recipe are those rules that we've written earlier. So let's just go through what that looks like. So we had our rule matrix, and we had some rules about what we want to hear. 3 dinosaurs, 1 vehicle. And we'll just call that the budget because, you know, it makes sense. It's how many we want to hear, how many we're allowed. And in terms of what the code does, it'll distribute that sort of slice to the various categories, it'll say, okay, we want 3, we want 1, or however. And if you are using this sort of system, it's quite useful to have some early error checking. So if you say, we want to hear 1 billion dinosaurs, that's probably wrong, right? That's going to cause problems later in production. QA is going to have to catch that. Just pop an error message saying, you have made a mistake. This number is too large. Straight to the sound designer whenever they make that change, and then the error is caught really early, and then they can make a much faster change. So this budget's going to say, okay, we want 1 vehicle. It's going to pass that to the recipe. And what's the recipe? Well, it's the rules about what's more important. And it's going to basically rank our dynamic audio objects, our sounds in the scene, and it's going to spend it on what's most important. And the reason we call it a recipe is because it's sort of a bit like a cookbook recipe, right? You've got these steps of what to do, like sort by distance, and then cull anything you can't see, and then make sure you hear the predator. And by breaking it up into these simple steps, easier to understand, less bugs. And when you're sort of building the code components from these, it's useful to use a predicate, like the closest predicate is more important than not predicate, rather than writing a new piece of code every time you want to have something for predators and prey. So let's just go over that sort of whole system again. We've got our triggering code. It's going to be saying, post this event, set this parameter. It goes into dynamic audio objects cache. We've got a budget saying we want 1 vehicle. The recipe ranks those dynamic audio objects, most important to least important. We want 1, so we connect up the top one because it's most important to the sound engine. It starts rendering, we hear it. But the least important one that we don't want to hear, we just use that cache. We don't use any performance, or very limited performance. Cool, so that's sort of a system, but what can you do with it? How is this sort of better than Wise? Well, we wanted to make sure that you could still do this sort of real-time budgeting, where you can change what the mix sounds like in real time. You can say, okay, I want 10 vehicles, what does that sound like? And hear it straight away, rather than having to rebuild and recompile. Make that change, hear it immediately. And also to make it's not particularly clear, but we render in game when an audio object is sort of virtual, when it's not using that performance, or when it's physical and it's rendering. So it's you don't even have to listen to the game to sort of see what's playing. You can just look at it and say, okay, why is that T-Rex not playing? It's red. I want it to be green. I want it to be hearing it. And another thing you can do with it is you can have different sort of budgets based on what's happening in the game. If you've got a soundscape that sounds really great for general gameplay, 4 dinosaurs and 1 vehicle sounds really good for most of the game, but you've got a dinosaur escape, there's loads of dinosaurs, and you want that cluttered mix, but only in that specific scenario. You can have a different budget and change to that budget depending on what's happening in your game. And the core of this system is the recipe. That's deciding what's important. That's building this AI that makes sure we hear what we want to hear. And traditionally in games that's just been whatever's closest to the listener, but it doesn't have to be. It can be things like if it's got using up a higher proportion of the screen space, if it's bigger on the screen, that's more important. Or you can write a rule that says if you've got too many of a specific species of dinosaur, they're not important. The 10th T-Rex is not important. You don't want to hear that many. Or similarly, if you've got too many in a specific space. If you've got a load of dinosaurs all packed into a really tight radius, and you've got one dinosaur that's running away, desperately trying not to be eaten, that's the important one. That's the one your eye's drawn to. That's the one a linear sound designer would pick. So you can make a rule that says, okay, if there's too many within a radius, ignore it, and then you'll create space for that important dinosaur. And yeah, it can also be gameplay driven, like if you've got a dinosaur that's breaking out of its cage and it's about to start mauling people to death, it doesn't matter if it's far away. It doesn't matter if it's quiet. It's the most important thing. That's driven by gameplay. And you can write a rule to make sure the player will hear that small, quiet, but very important dinosaur. And yeah, you can obviously extend this to whatever context you need for your game. If you can write it in rule format of this is more important, we don't want to hear, we do want to hear, you can add that context and make sure you hear what's important for your game. It doesn't just have to be what's closest to the camera.
Okay. Thanks, John. Okay, so we'll just have a quick video now of some in-game footage in a busy park, so you can kind of get an idea of how this actually plays out in the game.
Ladies and gentlemen, we are pleased to welcome a Gallimimus to the park. Ladies and gentlemen, we are pleased to welcome a Squithiomimus to the park. Ladies and gentlemen, we are pleased to welcome a Randosaurus to the park.
Senhoras e senhores, como medida de precaução e para sua segurança, prossigam para o abrigo mais próximo. ご来園の皆様に申し上げます。万が一の事態に備え、皆様の安全の確保のため、最寄りの次は
Okay, I think he wants his dinner, maybe like some of us. Okay, so let's evaluate this custom solution that we've developed. We used in Jurassic World Evolution. So run fast. Well, overall, we're quite happy with performance. So if we look at the audio render thread in WISE and turn off our system, so it's just the WISE voice management, and set it to something sensible like 64 physical voices maximum, the render thread is showing 120% in the authoring tool. And this means that we're not actually processing the voices in enough time for us to put it into the output buffer. So we're getting audio dropouts, basically. When we switch our code on, when we switch our system on, this 120% jumps down to 40%, which is quite reasonable. We're getting everything done in a really busy scene, plenty of time, lovely. So this is quite a big jump, but it's probably due to the kind of open world games that we make. In our busy scene example, we had about 2,000 game objects. So this is double what WISE recommend you have. And our game objects there's quite a lot going on with them. We're posting events, we're setting multiple RTPCs. Basically we're really squeezing as much as we can out of the engine. And the fact is that we just have to manage voices here. So that brings us down to a more sensible 40%. So our code obviously doesn't come for free. Like, we have to work out what to play. But our system takes around 1.5 milliseconds to process this each frame, which is well within the bounds of what we can do because we're doing this processing in a multi-threaded environment. This is absolutely fine in terms of the overall game frame. I think that the key thing here was that our single concern architecture made it possible to really optimize the code. The cache that John talked about, we could make sure that worked as efficiently as possible because each part of the system did one thing, so we could really focus and get it running quick. Okay, so how does it sound? Well, I mean, I think the audio team did a really great job with Jurassic. We're really pleased with the audio, how it sounds. The recipe-based the approach that we outlined before, it lets us be really aesthetic focused. So we're doing voice management because we want it to sound good, not because we have to claw back frame time like deep into production. So we could think of, more like how is this sort of AI mixer going to work? Like how's it going to react to these different scenarios in game? Thinking about it in terms of the domain of the game, not just things like, oh well, it's the closest 10. It's like it's the fighting dinosaurs. Those type of statements. So the other thing is that rather than just kind of hard kill sounds that we don't want to hear, our system lets sounds come back to life after we've killed them. So, if we said, well, that dinosaur's not fighting, so it's not important, and then suddenly he comes into life, the sound will kind of be resurrected rather than just not playing or doing something clunky like that. Okay, how about development costs? Well, the initial version of the system took about 3 months between 2 coders. This is quite a large investment, but it was it allowed us to hook when we came to hooking up the audio to that stage of production. It allowed us that to be super streamlined. We weren't having to worry about voice management. We could just worry about getting the animation to play audio, getting the terrain editing tool in the game to sound nice, these type of concerns. So, yeah, it was really handy to split those things apart. Because we kind of focused on this don't repeat yourself idea, when we did have a bug, I hold my hands up, yes, there were some bugs in the system, but when we did have a bug, we could just fix it once in the one place and not have to kind of, oh yeah, and then this 10th other place where we do the emitter management, I've got to do it there as well. There was none of that. Fix it once, be done with it. Okay, so yeah, I think the key, that all went well during production of this game, but the key win on the development cost side was that the system's now ready to reuse. Like we've done this in a generic way. We can reuse it on future games. We can port it back to existing games. And because it's not a brittle system, when we port it to a new game, we can just write the customizations we need. We've done all the heavy lifting of the underlying framework. That's ready to reuse. That's a really big win. Okay, so that's basically it. Just do a quick recap of everything we talked about. So we've got, voice management is key to good sounding games. I hope we've convinced you of that. Middleware solutions, they exist, you can use them. They can be problematic, especially when you have a complex game. But I think actually, it can be, these techniques can be really useful on a smaller mobile game. You might have smaller resource pool. You might want to, not just play the closest 5 things. You might want to do something a bit more creative. And really middleware solutions can't do that as easily, we find. Custom solutions can address these. The development of custom solutions is really helped by coding best practices. So what we mentioned before, don't repeat yourself. That's a really good one to follow. And separation of concerns, also really important. And yeah, the final point really is custom voice management solutions really make sense if that tech can be reused. So it's really worth investing the time to make something generic that you're not just going to have to write every project that you work on. And that's it. So are there any questions? Does anyone have any questions at all? Okay.
Do we have
no questions?
Do we have any questions? No.
There you
Thank
go.
you. Ah,
Yes.
yes, there is. Great.
Hi, I was interested in the rules you were mentioning before and how you wanted to make it more human readable as opposed to just numbers.
Yeah.
If it's possible, could you go into a little bit more detail about that, what it actually looked like?
Do you want to do something?
Yes, so basically we had, it wasn't like, I think a future extension of the system would be like a visual programming language that a sound designer could use, where they could slot in like, you know, sort by distance, flag for this things. But in terms of, we didn't sort of do that for this project, but that is definitely something we're thinking about. So at the moment it's sort of call like sort by distance in the code, and then, you know, maximum of this number of this type. And that was, we could, the way that the code looked was, you know, it was, I can't remember the exact name of the function, but it was sort of like maximum of this type equals 4 or whatever, something like that. So it was like, when you were looking at a recipe of how it sorts it, you could very easily read, okay, I'm sorting by distance, I'm making sure there's no more than 4 prey animals, and then I'm making sure I can hear the fighting dinosaurs. And then you didn't have to consider exactly how those functions worked under the hood. You could just read those sort of top-level statements. That was sort of how it worked.
Yeah, so for like the vehicle recipe, for example, we might say, we only ever want 2 helicopters, 3 jeeps, but if the player's in any one of those vehicles, then we want to hear that one. So we would come up with a kind of an informal spec, really, or you know maybe a formal spec, but that would then be implemented code side. But as John said, we think there could be merit to making a GUI-based tool where you could just visually see exactly the different component parts of a recipe and maybe move them around or sort of adjust or add a new thing. Yeah, that would be an interesting way to go with it, I think. Okay, anyone else? Any more?
Any more?
Okay, great. Thank you very much.
Thank you very much. Let's give a round of applause.